All right, so here we go. 3.1, we're starting a new chapter and it is all about derivatives. Okay, it is all about derivatives. Now, I know that some of you in here have already seen calculus before, and some of you have never seen calculus before. And so I think that that's one thing I would really encourage all of us to kind of be aware of, is that I think this content is definitely easier the second time round or the third time round. And the first time is so much like, what are we even doing? Okay. And so as we're talking to each other about these things, I think it is important to keep in mind that we need to give each other maybe a little bit more space than we had in the past to kind of like think through things and figure concepts out. Okay. Additionally, I think that there are some of us who are super, super good at procedures, like we've always been able to factor really quickly or do these procedures really quickly. But what might end up making calculus a little bit more challenging is that we focus also on the concept. And so not just knowing how to do a procedure, but when to use it and why that's happening becomes really important here, okay? So let's start off with this, what we know. So far, in theory, what we know is what a limit is. I believe we do, and how we find limits. And I think that I'd say we're about 75% of us are feeling pretty confident about like, how do we find limits and like, how do we know which strategy to use, okay? I would love that percentage to be 100% by Friday. So that second thing that we know, we've talked about continuity. So what is continuity? How do we know if something is continuous or discontinuous? Okay. And finally, I want to do a little bit of a throwback to this idea of slope. All right. And so I'm wondering, before we sort of move through the lesson, if you could tell me a little bit about what you know about slope, and let's kind of write down a few ideas. Okay. You can type it into the chat. You can unmute yourself and say whatever works for you. But let's throw down a couple ideas of what slope is. Okay, so y equals mx plus b is a representation of slope for sure. Rise over run. Okay. What else?
That could also be written as the change in y over the change in x.
Change in y over the change in x. Yep. What else do we know about slope? Steep. Okay, I like that word. So maybe we're looking at how steep something is. Steepness. Whoa, that's too many S's. It can be positive or negative. Can be positive or negative. Okay. Anything else? Well, I think that's a pretty good list to start us off, but basically the next 2 units, we're going to be studying slope for like weeks and weeks and weeks. And we're going to take a look at all different kinds of slope, okay? And we're going to use limits today to figure out how limits connect to the idea of slope, all right? So for those of you who took, well, everyone in here has taken trig, Math 104. One of the things about Math 104 that I think is really hard for students is that you learn the unit circle and then you're like, oh, well, that's not gonna come up again. It can't possibly come up again. And then you realize the entire course is really about knowing your unit circle and like all the different ways of using that. So I share that for the reason that, yes, we're going to be learning about slope for the next, several weeks. And it's really important to keep in mind the things that came before as well, but also building a solid foundation of slope here so that when we get to the second half of the course and we talk about area, that it's going to still make sense. Okay. But in 3.1 today, specifically, we're going to focus on two new concepts, okay? One called the average rate of change and one called the instantaneous rate of change. All right, so we've got an average rate of change and we've got an instantaneous rate of change. I have a perhaps unhealthy love for shortening phrases so I don't have to write the whole word. I might refer to average rate of change as AROC, just so I don't have to write it out the whole way. I might refer to instantaneous rate of change as IROC, instantaneous rate of change. Okay. All right. So I want us to take some time looking at this graph here. Okay, so we've got a graph and we have 5 questions with it. Okay, so let's take a couple minutes, and maybe because it is the first day that we've had class this week, just take a few minutes and write down our ideas for A through E. Okay. And it could be answers, it could be ideas, but you can send chats to each other. It doesn't have to be to the whole group and discuss this. However you want to do that, let's take a few moments and kind of try and answer these questions. Okay. All right. Do people feel like they've had enough time to think about these questions? All right. Well then, Isaac, thank you for kicking off our conversation. Okay, so we have these two graphs. I know this isn't necessarily the best picture, but if we think about maybe A, we can highlight for ourselves is sort of this line, and then B, we can highlight for ourselves is this one, right? So more like a banana. And yeah, I think, so Isaac says A runs at the same pace the whole way, unlike runner B. Okay. Now, Isaac, I'm wondering if you can share, or if someone else can share, how you know that A runs at the same pace.
So we're dealing with like meters and seconds, and we can think of this as velocity, which is meters over seconds. And because it's a constant line, it's like a linear slope. We know that it's a constant velocity since it's straight, and the more meters you go, the more seconds pass, and there's no change. Versus in runner B, there's a change in velocity, meaning that person accelerated. So how we can see this is that at first, runner B was running a bit slowly, and then as time goes by, runner B starts to accelerate, meaning they start running faster, which is why you have that little curve.
Okay. All right. Did I capture your thoughts appropriately? I think you framed that really well. Yeah. Okay. Anybody like to add anything to comparing the runners? Okay. All right. What about the average velocity of runner A? Anybody able to determine the average velocity of runner A?
10 meters per second.
10 meters per second. And how did you get that? You mind talking us through your process?
No. So each one of the squares represents 2 seconds if we're going horizontally across, because they're labeled every 2. And then vertically, each one is 20 meters. And so you can just half those 2 numbers and it's 10 meters per second. And then what I thought was really interesting is the fact that they both, one obviously holds that same speed. The other one, the speed changes, but because they finish at the same time, their average is the exact same.
Oh, okay. Well, I very much agree with you on that second point, Austin, that they start and finish at the same time, which means that they were able to cover the same amount of distance. But I would maybe disagree with the numerical value of your average velocity. Okay. So where are these numbers coming from? Do you mind unpacking that a little bit more? I would 100% agree with what Graham and I think Thea are saying, but I'm wondering if you can help us figure out where those numbers came from. Like, how do we find that average velocity? He traveled 100 meters in 14 seconds. Okay, so we know that they finish here, correct? And they start here. And so one thing that I think maybe will be helpful for future problems, even if we don't necessarily need it here, is exactly what Graham is saying. That idea of rise over run, or change in y over change in x, right? Those are things we know about slope. And so if we write down that formula here, we're going to get change in y over change in x, or some people might say rise over run, or yeah, we could think about y2 minus y1 over x2 minus x1, or however you want to write that. Okay, and so let's find those points. And I think that if we choose this last point here, we're going to end up with 100. And the x value of that point is 14. But since we start at the 0, we get 0 and 0. Yeah. And so I wanna just make sure that we're clear on this last point, is that yes, you can take a point and turn it into a fraction only if you start from the origin, right? And so this piece right here, the fact that it starts at the origin makes all the difference. But as we move forward, it's going to be really important for us to think about picking not just one, but 2 points that we can identify and use those values. Okay. So I know we don't need to write 0 over 0 and 0 here this time, but we might encounter other situations where that first point does not go through the origin. Okay. And so, yeah, we'll get 100 over 14, or let's reduce that to 57ths. And the units for this would be meters per second. Okay. Now, since Austin mentioned this, okay, so as a refresher of what Austin said, he said that the average velocity of runner A is actually the same as the average velocity of runner B. Because they start and they finish at the same time and the same distance. So we can actually say this whole piece happens to be the same points for runner B. Okay. And if we were to write that out, we could say it's the same as runner A because they start and stop at the same time. So I think, Austin, that was a really valuable observation that you had there. Okay.
Thank you.
So far, we're just using this idea of slope and saying, okay, we know it's rise over run, blah, 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 finding that slope. Sorry, Austin, were you going to say something? Or was someone else?
No.
Okay. All right. Are there any questions so far about how to find that average velocity? Okay. All right. So then let's take a look at the velocity when it's the slowest and when it's the fastest. All right. So what do we think about part C versus part E?
For runner A, because it's a constant velocity, there's really no fastest point. And I guess we're at the origin, it's pretty much the slowest because there's no speed, but it's constant velocity, so they're pretty much like no slowest or fastest.
Okay, so always running at that 57th meters per second. I agree. Okay. And what do we think about the velocity of runner B? When is that the slowest and when is that the fastest? Maybe we can look back in at this picture a little bit more carefully. When is it the slowest for runner B and when is the velocity the fastest for runner B?
One thing that I found helpful is like kind of looking at it as like ratios and kind of like what he's saying right there, pretty much towards the beginning and is where it's like the slowest, and then towards the end is where runner B is the fastest because they accelerated faster.
Yeah, so like the slope down here for runner B is kind of flat. But then as we get up here, like the slope of that part is steeper. Right? And so I think both Graham and Natalia saying sort of at the beginning, runner B starts a little slower. At the end, runner B is running faster is a pretty accurate description. So slowest at the start. And we can say that's the least steep slope if we were to include some vocabulary from earlier. And then the fastest is at the end. And we're looking for the most steep slope. Okay, so the least steep and the most steep is sort of what we're looking for visually here. And I don't know how many of you in here are relatively tall or maybe have long legs for your height. which is so weird. I feel like because I've never actually seen some of your faces. But if you have, okay, so if you have longer legs, like really long legs, sometimes it can be harder to move them more quickly in the beginning. And so like I used to play rugby, and I had a teammate who was very tall and she was very fast, but only as we got towards the end of a sprint, because her legs were so long, it took her a while to sort of get up to speed. Whereas you might imagine like, the typical sprinter. The typical sprinter is a little bit taller or a little bit shorter. And because they're shorter, they're able to sort of move their legs a little bit faster because they're just less to move. Okay. So that is something to think about, like as you're looking at this picture, how does that relate to a scenario that you can imagine? I played flanker and hooker for a bit. Graham, did you play? Oh, cool. What position do you play? Nice, nice. All right. So let's move on. Let's take a look at rates of change, okay? So what I'd like to do is to go through one of these together, and then maybe put you in some breakout rooms to work on some of the other ones. But what we're really focused on now is, let's think about rates of change as an idea as it applies to a graph and kind of how we can tell, okay? And so in this case, in example 1, it says, here's a graph, right? And it says, draw a dot on the graph where the x equals 20. Okay. So are folks able to annotate on my screen? Do I have to change the settings? Ah, there we go. Okay, cool, cool. All right, so at x equals 20, draw that dot on the graph. Okay, great. And what is the y value of that point? Oh, a shining star. What is the y value of that point?
About 300?
Yeah, I would say about 300, right? Okay. What about part B? What is the draw a dot on the graph where the x value is 60, and what is the y value of that point? Yep, I agree. So we've got 700 about, okay, give or take. Okay, now find the slope of the line that connects the 2 points that you drew, okay? So if we wanted to put that visual in so perfect, we would connect those 2 points, okay? And now the question is, just go ahead and find the slope of the line there, okay? And so I think what we can do is actually go ahead and use that same formula from before and plug in our points. Okay, and so this is why we want to make sure we know that we're plugging in 2 sets of points and not just 1 set, right? Because sometimes it doesn't go through the origin, right? And so it doesn't really matter which one you have where, but if I put the 700 here, what number goes down below the 700?
60.
Yeah, the 60, right? Because these 2 together should make one of the points. So 60 and 700 is 60 and 700, which is that point right there, right? Now, similarly, if I plug in the y1 and the x1, I'm going to have 320. And that's because we have our point here, and here's our 320, here's our 300 and our 20. All right, so we do a little computation. We get 400 divided by 40, and we end up with a slope of 10. Okay. All right, any questions on that problem? You're totally fine. I know it's such a small thing, but I'm actually really glad we can annotate and sort of like work together on this board. It makes me feel a little bit less lonely sometimes. Okay, so any concept questions or procedural questions on example 1? Okay, if this all feels pretty familiar, this is good. It's a really good start. Okay, but let me just show you, we have a few other examples. So example 2, example 3. Okay, and so what I'd like you to do is I'm going to put you in some breakout rooms, and we're going to take maybe about 10 minutes to work through the examples. And I want you to stop when you get to where it says average rate of change. Okay, so when we get to average rate of change, you're going to stop, and then we'll come back, we'll check over this work, and we'll summarize this first chunk of today. Okay, so let me go ahead and stop sharing my screen here. I'm going to, okay. So I did a little bit of some stuff here, not a ton, but we have that, for example, 2, did you all get something like this? I see a couple yeses. All right, all right. Were there any questions about number 2? Okay.
I have a quick question just to confirm. When the slope is going downwards, like it's going in the, yeah, it's going downward. The slope is always negative, right?
If you are reading from left to right, so you're going like this way across your screen. If
Yeah,
the line
that's
goes
what I meant.
down, then yes, it is negative.
Okay, cool. Thank you.
All right. That's a good clarifying question though, right? We want to make sure we remember some of these things, that like something like this would be a positive slope, but something like this would be a negative slope. Okay.
If we were ever to draw the line on the graph, would we get marked off if we drew a line segment, which is like to the point, not like arrows?
Oh, no, that's fine.
Okay.
Yeah, you're fine. Okay. All right. So then the next few questions are really about like thinking a little bit more, less computational, but thinking about comparing graphs of slope and things like that. And so I'm wondering, for part A of example 3, what did people get in their groups? Maybe we can zoom out a little bit here so we can focus on just the graph, but the question is asking us to identify 2 slopes where the slope, or 2 points where the slope of the line connecting them is 0. So if you and your group came up with something, I'm wondering if you could sketch that on the graph right now. Where might those 2 points be? Okay, so Richard, it says it looks like 10 and 400. Cool. Exactly. I think that works. This is maybe the most dreaded question or follow-up question in a math class, but what else? What else works? Ah, okay. So
I was going to answer any 2 points that are they're intersecting a horizontal line on the graph.
okay. So like this one is the first one that a lot of groups picked, which is awesome. And then we saw someone who said, oh, maybe here. And I would agree. That's maybe another line. Give me one more. Very nice, very nice. This piece up here, Chance, right? So these are 3 possible options, okay? Now I know that as math students, some of us have had a love for math because there is one right answer. We're going to kind of blow up that notion a little bit in this class in the sense that there may be more than one answer. But what I really love, Ethan, about what you said, and I'm going to write that down. So I'm going to zoom back in and write down what you said. You said that the y values are the same. Could you rephrase that for me?
Yeah, it would. I said any 2 points that a horizontal line intersects, which is essentially a different way of saying what you said with any 2 points that have the same y value, because there's going to be no change in y.
Perfect. So any 2 points that a horizontal line intersects, that is the 2 points have the same y value. Okay. Okay. There's a couple key concepts here that are going to come up again and again. One of them is that a horizontal line has a slope of 0. Okay. Horizontal line has a slope of 0. We're going to be leveraging that idea to solve problems in the future. Okay. So a horizontal line has a slope of 0. And the bigger idea here, we could draw so many lines that have a slope of 0. But the bigger idea here is exactly what Ethan expressed, which is any 2 points that have the same y value are going to make this true. Okay. And this right here, like the way that you've all been able to contribute to this, like multiple ways of showing one answer, okay, one possible answer, and connecting it to a bigger pattern, like describing that they're all going to have the same y value, that is a really, really good way to approach the content that we're going to be going over, okay? So as a learner, I think those are really good skills. All right, what about, I just found out that I have a pointer now on the thing. I know, so I can be like over here and you can see the red dot. That's pretty cool. Okay, so there were 3 other ones. Whoops, there were 3 other graphs. Were there any of these graphs that folks felt tripped up on or would like to go over before we, and I can clear them too, I think. Okay, so of these last 3, were there any that groups got stuck on that you would like to see before we move on? Or do you feel pretty confident about them? So the slope of a certain x interval would just be that y point over the x point. The difference in the y's minus the difference in the x's. Does that help, Richard? Oh, okay. I see. Okay, so let's take a look at C and D. So the slope at 10. I'm wondering if I can have a brave soul who might want to sketch the slope at 10. Like, what does the slope at 10 look like? Everybody see that? Okay. All right. Now let's pause here for a moment before we look at the slope at 30. But at x equals 10, tell me about the slope. Is the slope positive? Is it negative? Is it 0? Let's just kind of start there. What would you say about the slope at x equals 10? Okay, that it's a negative slope. Okay. Now, maybe some of the folks who did not draw the sketch for the slope at x equals 10, I'm wondering if you can try and using what you see for the slope at x equals 10, draw what you think the slope might be at x equals 30. Okay. So if you were on the fence, you're not really sure what it looked like, but now you see an example, what might you think is happening at x equals 30? No brave souls. Looks like we have sort of two competing ideas here. So I'm not going to zoom in because then I'll lose what you have. But I noticed that someone drew one that was kind of like this, that yellow line. Here, maybe we'll go over it a little bit thicker. That yellow line. And then it looks like someone else is saying that maybe it looks more like this. Well, it turns out that when we are, as Richard pointed out earlier, looking for the slope at a single point, okay, we almost have to, gosh, whoever said this as a description for limits, I think that was like the best word that we can continue to use here, which is, what if we zoom in on what we have, okay? So I'm going to erase what I have and Awesome, thank you. And let's kind of zoom in here. Now at 10, okay, at 10, I know that the point is like here, right? So if I want the slope at 10, I really want to think about what's happening as I get really close to 10 slope-wise. And so when I'm getting really close to 10 slope-wise, we end up with something kind of like this. Okay. So do you see how that pink line just kind of just touches the graph right at that one point? And I think that Natalia even said it's like a tangent line. It touches the graph in just one place, okay? Now, if we use that same idea to think about what's happening at x equals 30, okay, at x equals 30. So x equals 30 is right here. If I were to draw a line that describes the slope of this curve right at this point, it might look something like this. Because I'm just thinking about the immediate area right around x equals 30. I don't care really what happens at like 40 or 50 or 60 or 20. I want to think really carefully about what's happening at x equals 30, like as close to 30 as I can get. And so now if we kind of zoom back out, I think Ethan, your picture before we erase the annotations is probably far better than mine, but the orange line is a little bit less negative. Like I would say it's still negative, but it's less negative slope than x equals 10. Okay. So I appreciate that folks asked about this because I think that's actually exactly the point of this exercise. So let that sit for a moment and then let's kind of think about what questions we might still have. So we didn't actually answer the question yet. We said the question is the slope at 10 larger or smaller than the slope at 30? So what do we think for that particular answer? Is the slope smaller or larger?
It's smaller because it's a bigger negative number.
Okay.
So it's smaller. So it's like, it's steeper, but it's actually smaller than the other one because it's negative.
The slope at x equals 10 is more negative and therefore smaller than the slope at x equals 30. Okay, so the slope at x equals 10 is more negative and therefore smaller than the slope at x equals 30. So let's see, there's a question in the chat. So the point of the line is to get as close to the graph on both sides of the x interval as possible while only intersecting with one point. Welcome to calculus. That is maybe one of the best summaries I've seen of what we're just talking about. Okay, let me read that one more time, folks. So the point of this line is to get as close to the graph on both sides of x. And let's see, where have we seen this idea of things getting as close as possible? Ooh, maybe something to do with limits, right? So we're trying to get as close as possible to both sides of that x interval so that we can estimate what's happening at one single point. Okay, that is very, very well done. All right. Let's talk through D real quick, because I know there were some other questions on that. That conversation might go a little bit smoother now that we've seen part C, okay? But in part D, the question says this: which is larger, the slope at x equals 60 or the slope of the line connecting 40 to 80? And so let's take a look at my artwork here. We're going to take a look at the line connecting 40 and 80. 60, 80. Something like that. Okay. And the one that is the slope at 60, so 60 is right here. Now, before I draw it, what are our guesses? Is the slope at 60 bigger, equal to, or smaller than the slope of the pink line? Bigger, yeah. And check this out. If I work on my artistic skills here, I can see that this orange line is steeper than the pink line. Okay, and Natalia, to kind of go back to your earlier point, do I care whether you draw a line segment or a line? Not really. I tend to draw lines because it's easier for me to compare sometimes, but really that's up to you. It doesn't have to be one way or the other, okay? All right, so I would say the slope at x equals 60 is greater than the slope between x equals 40 and x equals 80. Okay. All right, what other awesome things are we having in this chat? If we could find what, I can't read. If we could find what the point is at the single point we are dealing, and we are dealing with an x versus time graph, we can start to find what the velocity is at the exact time. Great connections to a very sort of innocuous thing that we started with, right? Let's kind of go back to where we started from. Woo! Okay. We started with a picture that I would say that most of us probably felt pretty comfortable looking at, right? That we knew that A was a constant velocity. We knew that B was different. And I believe it was Austin who made that really great generalization of what's happening between runner A and runner B, right? And we were thinking about this as it applies to velocity, like how fast do you run? Who's the winner, right? And we've seen these kinds of things before in math. And we've also seen these kinds of things where we're like trying to find slopes between points and find slopes between 2 points and slopes between 2 points. And we're finishing with this idea of the slope at a single point. Okay. That is exactly what we're going to summarize right here in this average rate of change versus the instantaneous rate of change. Okay. Now, I know that it is pretty close to 11. We've been going for quite some time with this math. Would we like a break right now? And then we can come back and finish 3.1 and 3.2, or would we like to finish 3.1 and then take a break? Break, please. Absolutely. Okay. So let me stop the share. And we looked at slopes between 2 points, and we looked at slopes at a single point. And so that leads us to the very foundation of Unit 2, which is right here in this next page. Okay. So we're going to take a look at the average rate of change, and then we're going to compare that to the instantaneous rate of change. We're going to start with a picture. We will layer on some vocabulary, and we'll include a formula for both average rate of change and instantaneous rate of change. Okay. So for average rate of change, I'm going to say, let's just draw part of a function. Okay. And so let's say we had a function that looked like this. And we can call this f of x. And I'm purposely not putting it on a grid because it could be anywhere on the XY plane and it would still be okay. And so let's see, let's choose one point here, somewhere on the curve. And let's say that this has an X value of A. What is the Y value at that point? How would we express the Y value at that point? Not B, but I will use B for the next point, f of A. Yeah, we're going to call this f of A. Okay. Now, Yithan, you've jumped the gun here. You said, oh, we're going to talk about the second point. So let's put another point somewhere else on our function. All right. And we will give this point an X value of B, and then it follows that the Y value there is going to be f of B. Okay. So we've got A, f of A, B, f of B. And now if we say, let's find the slope of the line that goes through both these points, we could diagram that like this. Oh, not bad. All right, so we've got this line that passes through both points here. Okay. Now this point, I'm sorry, this line has a specific name. Okay. So this blue line is called a secant line because a secant line passes through 2 points on the curve. Okay. So here's what we're going to write out in words, but this is our visual. To find the slope of the secant line, we can use m equals y2 minus y1 over x2 minus x1. That's something we used in a lot of the examples before, but we used rise over run to show us the slope, right? The slope between 2 points. Additionally, this is equivalent to the average rate of change. Okay. That is, we can say that average rate of change. So here's where I'm going to abbreviate. AROC, average rate of change, is the same as, and let's use the notation from our picture, F of B minus F of A over B minus A. All right, so I know that was a lot of writing, but I'll give you a moment to finish writing that down, copying that down, and let's see if there are any clarifying questions before we move on to the instantaneous rate of change. All right, so far so good here. Got a yes. It's okay to say no. It's also okay to say yup. Okay. So average rate of change is not something terribly new to us, okay? But what's useful about starting with the average rate of change is that we can use this to talk about the instantaneous rate of change. And so what I'm going to say here for the instantaneous rate of change is going to be a little bit more of a dressed up formal version of what Richard actually said really well earlier. Okay. So we're going to do the same thing. We're going to draw a picture. We're going to label it. We're going to add some vocabulary. And then we're going to describe in some sentences how this is similar, but also a little different from the average rate of change. Okay, so the instantaneous rate of change. We're going to draw a function, random function. And every time I say random, it always comes out looking like this, but here we go. Okay, so I've got my function. I'm going to call this f of x. But this time, instead of having 2 points, I'm only going to draw 1 point. Okay. And what I'm going to do with this 1 point is I'm going to sort of sketch a line that touches this curve at just 1 point, just this orange point. Okay. And this line is called a tangent line. And we used that word earlier, but a tangent line is just a line that touches a curve in one place. And that's different from the secant line, which crosses it in 2 places. Okay, so secant is 2 places, but tangent is just 1. And so we're going to call this point x comma f of x. Okay, so the coordinate of that point is just going to be x f of x. But if we wanted to find the slope of this line, what we can do is actually use the idea of slope between 2 points to figure this out. Okay. So I'm going to take this picture. I'm going to zoom in a little bit more. So if I draw this part of the curve and I have my point x comma f of x, okay? Now check this out. I'm gonna pick another point on the curve. I'm gonna pick this point so that it is really, really close to the orange point. Okay, so I've got my original point and then I have a purple point that is like really close to the orange point. Now, if I were to graph or connect these two with a secant line, that secant line will actually have a very similar slope as the tangent line. What happens, do you think, as the purple point gets closer and closer and closer to the orange point? Does that make the slope of the blue point similar or more different from the orange line?
Very similar.
Okay, so if we took this point and we kept moving it closer and closer and closer to the orange one, we would effectively be saying, let's use the slope formula, but with 2 points that are super close together. Okay. So this is the conceptual piece, okay? To find the slope of the tangent line, okay? To find the slope of the tangent line, use m equals y2 minus y1 over x2 minus x1, where x1, y1 is really close to x2, y2. Okay, so let me read that again while you're writing it. To find the slope of the tangent line, use m equals y2 minus y1 over x2 minus x1, where x1, y1 is really close to x2, y2. This is the same as saying instantaneous rate of change that is we're gonna write down the following formula, okay? So the purple point that we have here, okay? I'm gonna give this a coordinate. I'm gonna call it x plus h, meaning x plus a very, very small number, h, okay? Now, if x plus h is the x value at that point, what can we say is the y value of that point? Perfect. Very nice, George. Very nice, Megan. F of x plus h. Okay. So that idea of function notation doesn't change. We're just plugging in something that's like x plus h, the unsimplified version, right? Because we don't know what x is, we don't know what h is. So we just have to take that whole x value and plug it into the function, okay? So check out what this does to our slope formula. Slope equals, okay, instead of y2, I'm going to write f of x plus h. Instead of y1, I'm going to write f of x. So we've got this y value from our second point and this y value from our first point. And I have to put this over the x value of the second point minus the x value of the first point. So first point, second point. Okay. Now let's take a look at this. If I want the 2 points to be really, really close together, what might be a possible number for h? Okay, what might be another possible number for h? Really, really close though. Yeah, more in that direction. Okay, so we're sort of weirdly in a point where like 1 is not necessarily a small number anymore. We're thinking like a whole lot of zeros and a decimal point and then like a number. Yeah, well, it doesn't really matter. And so that's why we could have one exactly, right? So thank you, Ethan. I'm too lazy to type these in myself, but it could be any of these, right? Any of these work for h. But if I ultimately want, if I ultimately want h to be infinitely small, what value do I want h to get really close to? Okay. So if we had the purple point be basically on top of the orange point, h would be 0, right? That distance between the two would be 0. This is where the idea of limits helps us, okay? We can say that the limit as h approaches 0, so not x, but h, because the h is the distance between the 2 points. So if we take the limit as h approaches 0 of our slope equation, okay. Now let's simplify this a little bit. I don't know what the numerator is, so I'm going to keep it in function notation. But what does the denominator simplify to? Okay, right? X plus h minus x leaves us with h. Good, good, good. Okay. Now, what's that go to? Like when you get to that test on Friday and I'm like, find these limits, what is your number one strategy that you're going to try first before you do anything else? You're going to substitute. Okay. So you are going to plug in or you're going to substitute before you do anything else. So with this equation, I'm going to use my new pointer. With this equation right here, what happens when we plug in 0 for h? Exactly. When we plug in 0 for h, we're going to get an undefined. And so when we have something that's undefined, we need to think about different ways that we can sort of manipulate things. Okay, so like factoring, like we did before, or maybe complex conjugates, like we did from before, or complex fractions, like we did before. Okay, so all that stuff that you're going to study for Friday's test is actually helping us in this new unit as well. Okay, because while this is the definition of instantaneous rate of change, if we're trying to compute it, then sometimes we run into some issues where we end up with an undefined. Okay, but this bottom line right here, when we think instantaneous rate of change, we want to be thinking use the slope formula, but make the points get really, really, really close together. Okay. So before we move to 3.2, let's take a look at both these pictures on the same page real quick. What is one takeaway that folks have from the comparison of average rate of change versus instantaneous rate of change? And the takeaway could be something you learned about how to compare them. It could also be a question that you still have about average rate of change, but the instantaneous rate of change. Okay, so I see one comment in the chat that it's the same thing, but small. Okay. They both require 2 points, but the distance between them determines which formula you use. I love that. Exactly. So if we're just saying any 2 random points, great. But if we're saying at a single point, so as soon as someone says at a single point, which formula are we thinking we want to use? Average rate of change or instantaneous rate of change? Exactly. As soon as we say at this moment, at this one point, at x equals a number, just one number, we're thinking instantaneous rate of change. But when someone says, here are these 2 points, find that slope in between, they are secretly saying average rate of change. Okay? So let's